In this video, I covered the last subsection in the week 9 lecture called simply other topics, and those are, let's say, small topics that I found hard to fit somewhere else, and they're perhaps slightly less important than other things we've covered, but still, let's review them. And just note that although they are in the set of slides for Archimedean copulas and copula fitting, they are kind of standalone small topics. So they have nothing to do specifically to copula fitting or Archimedean copulas. The first thing is simply a alternative formula to compute Kendall Tau from a bivariate copula. And so the formula is here, but the setup, we need to be a bit careful to understand how the formula applies. So let's read the result. Kendall's Tau between any two continuous random variables depends only on their copula C. Oh, yes, this is something we've already mentioned. So just denote here as before tau, but tau C, just to highlight that it depends on the specific bivariate copula we have. So assume that U1, U2 is a pair of uniforms, so specifically uniform 0, 1 random variable that have this this copula C. So those random variables, they're not independent, they have a specific dependence characterized by the copula C. Now, this is the slightly tricky part. With C, big U1, big U2, seen as a random variable. So of course, C is a function, but if you feed to the two arguments of the functions two random variables, in this case, U1, U2, well, you have a function of two random variables. It's again a random variable. You can think of this the same way as if you have the univariate CDF, okay, the CDF of any random variable X, if to the function you feed a random variable big X, okay, well, this, you can view this as a random variable. And in this specific case, if X is continuous, you know that this is a uniform 0, 1 random variable. So this is the same kind of idea. We put as argument to this copula two random variables, but specifically random variables that are uniform with the dependence given by the copula C. Okay, and seeing this object as a random variable, you can compute its expectation. Well, yes, because careful, although this is a bivariate function, the result, this thing is just a number, right? It's not multivariate, the result of the function. Okay, so this is a random variable, so you can take its expectation. And this is the result, the new formula, if you want, to compute the Kendall's Tau. It is a function of the expectation of this random variable. So it is given here. Again, let's just summarize what this is saying. You have two random variables that have the copula C. Okay. Create a pair of random variables with this copula as their dependence. Let C of those two uniforms be its own thing, okay, its own random variable. 4 times the expectation of this random variable, minus 1, gives you the Kendall's Tau of the copula in question. Okay, now we don't prove this result, but the proof is not especially hard. You can look in the book, well, the book I use as a reference here, the Quantitative Risk Management, chapter 7, at some point they prove this. So anyway, that's the first little smaller result. But now there's another thing I want to present. It's somehow linked. It's this concept of the Kendall's distribution function. So let's review that. Kendall's distribution function. So we start with the definition. Let's consider the same new object we defined over there, this C of U1, U2, where U1, U2 are two uniforms with the copula C as their dependence. Well, it's as I said, we view this thing C as its own random variable. So you can find, in principle, you can find its CDF or its density function or everything you like. In this case, we use the expectation, but here we define simply the CDF of this random variable, and we call this Kendall's distribution function. So take the probability that this random variable is smaller than whatever argument little t. Okay, so you see that this is in fact a CDF, little t here. Okay, and this is a function of one argument, little t. Okay, in notation, we have big K C, again, C denotes the copula, and we call this the Kendall distribution function, which obviously depends on a specific copula. Okay, so the Clayton copula with a given parameter would have a specific function for this. The Gumbel would have a specific function for this. So it's a function that depends on the copula. And again, it's the CDF of this object CU1, U2. Again, CU1, U2 is seen as a random variable, so it makes sense to have the probability this random variable is smaller or equal to whatever small argument, whatever argument t here. Okay, now it is a sort of theoretical object. It's I don't know if there's a clear meaning to this that you can use in practice, but it can be used in proofs, but also it can be used for a goodness of fit test. We're not going to present this, but I'm just telling you that this thing could be used for goodness of fit test, but I'm going to try to highlight why is that. So, but just here as a comment, so this is a function. It's a function of the argument t. Now, because c is between 0 and 1, here it's a function for t between 0 and 1. But so, and it depends on the copula. So different copulas will generate different functions here given by this definition. So in a sense, because it's a function, it gives you more information about the dependence than a single number. Meaning from any given copula, you can compute Kendall Tau, but this is one number. And of course, you can have a Gumbel copula with a tau of 0.5. You can have a Clayton copula with a tau of 0.5. You can have a Frank copula with tau of 0.5. So tau gives you limited information. It's just one number. In the same way, just the expectation of a random variable gives you some information about the random variable, but not the full information. Here, this thing, because it's a function, it gives you more information. And we'll see a picture in a second. Just as an example, in the independence copula, it's not too hard to derive this function specifically for the independence copula, and you get the following function, t times 1 minus ln t. Okay, and let's just, I think we'll do the calculation in a second, but just for your reference here, if you compute this for the Gumbel copula, you're going to get a different function, of course. And then, in the case of the comonotonic copula, another example, remember comonotonic copula means a perfect positive dependence, so the two random variables increase in each other, not necessarily in a linear way, but could be a convex function or a concave function, but they increase in each other. In this case, you have simply that Kendall's distribution function is a straight line, just t. But so then, let's see on a plot what this looks like. For this only displays, so in the independent case, so the red line is the function over here. Again, it's a function of only one argument t, and t goes from 0 to 1. And then the comonotonic case is simply the straight line. But let me just show you one more plot, and for this I need to go to R. Okay, so here I've simply implemented a few more. So I've implemented the Gumbel Kendall distribution function and the Clayton, and I give to them arguments that make the Kendall's tau be a 0.5. Okay, and then here those are just the commands to draw the plot that we already see on the right. Okay, and so this is what you get. And so here you have a comparison, and the point is this: even though those two lines, the kind of yellow one, and then which is the Gumbel, and the Clayton one, which is the black dashed line, both have the same Kendall's tau, 0.5. No, sorry, no, 0.75. Sorry about that. This is exactly the same numbers as I use in the lectures. So a theta 4 for the Gumbel and a theta 6 for the Clayton yields Kendall's tau of 75. But you see the lines, they're quite different. Okay, they're quite different. In fact, you might remember that the Gumbel is as upper tail dependence. And you see that for large values of t, the Gumbel is closer to the comonotonic case than the Clayton, but the Clayton is kind of the other way around. It had lower tail dependence. And so for small values of t, you see that the Clayton is closer to the comonotonic case, while the Gumbel is not as close to the comonotonic case for small t. So you see it's a function, so it gives you kind of more information. But lastly, maybe I'll make here the comment I wanted to make. we don't present this here, but there's a way to find an empirical version of those function, of this function, the Kendall's, the Kendall distribution function. So you can use this as the basis for a test of goodness of fit for a specific copula, because if you want to test, for example, that your data comes from, say, the Clayton here, the black line, the Clayton copula with 75% Kendall Tau. Well, you can obtain an empirical version based on your data of the Kendall distribution function. And you see that if in your data, the function is close to the theoretical one, the one you think is a good fit for your data, well, then maybe you won't reject that this is a good fit. But if the function is very far away, okay, if your function is far away and maybe it's closer to the independent case, then you might have enough evidence to reject a specific model. Okay, but this is just a side note to explain that this is kind of a theoretical function, but it's one possible application of it, which is the goodness of fit test. Okay, back to the slides. I think that's pretty much all I want to say about this. Here, there's just a specific example. So, yeah, but one more formula. And again, this is the kind of formula I would give you specifically in the exam if you ever need it, because I think it's a bit hard to memorize. This Kendall distribution function is not tied to Archimedean copulas. It's defined in general. But in the case of Archimedean copulas, you have a neat formula to explicitly find the Kendall distribution, meaning you could find it just by basic principles, applying this definition, but you have a shortcut, T minus the generator of an Archimedean copula divided by the derivative of the generator gives you Kendall distribution function. So for example, the example we mentioned before for the Gumbel, we presented that the generator was this, minus ln t to the theta. So you can derivate this once, you get the derivative here. And then on top, you have then the generator, you divide by the derivative, you get a t on top. Maybe I'll let you double check that those simple calculations are correct. Okay, and you get a minus ln t to the theta minus 1 on the bottom, but then some things cancel out, because minus ln t to the theta cancels the minus ln t theta here, so you're left with minus ln t to the minus 1, but you put it on top, it becomes just ln of t. Okay, so this is one specific derivation of Kendall's distribution function for the Gumbel. And I think you can see that I think we said that, yeah, if theta is 1, this is in fact the independent case. And let's see, imagine that theta is 1, this cancels out. I think this matches the formula we had here, yeah, for the independence case. And if theta is very big, well, if theta is very big, this is going to be close to 0, and then you're going to get close to t. And indeed, t is the comonotonic copula. I think we mentioned before that the bigger the theta, the more stronger the dependence in the case of the Gumbel copula. Okay, and just for your reference, there's an example with the Clayton copula that derives this function in the appendix. But for now, I think I'll stop here, and I'll catch you in the next video. So thank you very much for listening.